Hi everyone, in this video we will learn a new method to find the largest or dominant eigenvalue and the corresponding eigenvector using the power method. Now what is a dominant eigenvalue? If you still remember, we had this equation matrix A multiplied with the eigenvector is equals to lambda multiplied with the eigenvector. Now, lambda is also known as the eigenvalue. An eigenvalue is a number and it could be either positive or negative. Now, imagine if we have lambda 1, lambda 2, lambda 3 up to lambda n as the eigenvalues of a n by n matrix A. Lambda would strictly be a dominant eigenvalue if lambda 1, the absolute value of lambda 1 or the magnitude of lambda 1 is greater than all other lambdas. So it's greater than the absolute value of lambda 2 and this is greater or equals to the absolute value of lambda 3 and so on up to lambda n. An example could be lambda 1 as negative 10, lambda 2 as 5, and lambda 3 as negative 5. So the absolute value of negative 10, which is 10, is greater than 5 and 5. Another example could be lambda 1 is equals to 2 and lambda 2 could take the value of negative 0.5 and lambda 3 could take the value of 0.05. Before going through the steps that we would take in the power method, I would like to start with an example because this is the easiest method for me by far to explain the process. Okay, in this example, we would be using the power method to determine the dominant eigenvalue and corresponding eigenvector for a 2 by 2 matrix A, where the stopping criteria is 0.01 and the initial vector is given as 1, 1. So whenever we have a stopping criteria and an initial value or an initial vector, in this case, then the method that we are discussing would be an iterative method. So it starts with an initial value, or in this case, an initial vector. So V0 is 1, 1. So this is the first step, writing out the initial vector if it's given. Now, if the initial vector is not given, then we would select an initial vector ourselves, but please ensure that the largest entry, the magnitude of the largest entry must be equals to 1. You may select V0 as 1, 0.5 or 0, 1. Okay, just make sure that the largest magnitude of each entry in the vector is equals to 1. Okay, next, the second step, we would be computing AV. So AV naught would be 1556 matrix 1556 multiplied by V naught vector 1 1. Now I find it so much easier using the calculator to calculate the values of the multiplication of these matrices. So a 2 by 2 matrix multiplied with a 2 by 1 vector gives us a 2 by 1 vector, which is 6, 11. In step number 3, we need to find lambda 1. So we are moving on to the next step. Now how do we find lambda 1? Lambda 1 is the entry in AV which has the largest magnitude. So the largest magnitude in this case would be 11. And next, we need to find the value of V. And how we do this is, in the previous video, we had AV equals to lambda V. So in order to find my new vector V, I take 1 over lambda multiplied by AV because I have the value of AV. So in step number 4, I would be computing V using the formula 1 over lambda multiplied by AV. So 1 over lambda 11 multiplied by the vector AV 6 and 11 gives us 0.5454 Okay, so that is step number 4. Now, step number 5 is the computation of the error. If you still remember, this is the infinity norm where we take the current eigenvector minus the previous eigenvector. So this would be, I need more space, so I'll use the space here. This would be the current eigenvector is 0.54541 minus the previous eigenvector 1 1, and the infinity norm of this is the set of the magnitudes of each element. So 0.5454 minus 1, we get negative 0.4546, and 1 minus 1 is 0. So the maximum of the elements in this set would be 0.4546. Alright. Now the error is always positive. And next, we would continue the iteration again. We compute our new AV1. So the matrix A remains as 1556 multiplied by our new V, V1, 0.5451, and using our calculator, we get 5.5454 and 8.727. Now we will be continuing the iteration until the value of the error is less than 0.01. So in the second iteration, our new lambda would be the entry with the highest magnitude, which is 8.727, and V2 would be 1 over lambda 8.727 multiplied with AV 5.5454, 8.727. So this gives us 0.6354 and 1. So AV2 would be, A remains the same, 1556 multiplied by the new V, 0.6354, which gives us 5.6354, 9.177. So we could find our new lambda by taking the entry with the highest magnitude, which is 9.177. But before that, I forgot to calculate the error, the infinity norm. So that would be this value, 0.6354 minus 0.5454. Because 1 minus 1 is already 0. And this gives us 0.09. Now we need to continue the iteration up to when the error is less than 0.01. So our new V3 would be 1 over 9.177 multiplied by AV. And this gives us 1 here at the bottom and 0.6141. Again, we could calculate the error. So 1 minus 1 is 0. I would take this value minus this value, the absolute value of it. So 0.6354 minus 0.6141 gives us 0.0213. So we need to continue more iteration because it's not less than 0.01. So again, we have AV using calculator. We get 5.6141 and 9.0705 as the second entry. So in our fourth iteration, lambda would be the highest magnitude of the entry, which is 9.0705, and V4 would be 1 over lambda multiplied by AV, and this gives us 1 here, 0.6189. And now we could calculate the error. 1 minus 1 is 0. We ignore that. And this value minus this value, the absolute value of it is 0.0048. Okay, let's look at the stopping criteria. The stopping criteria is given as 0.01. And if our infinity norm or our error is less than 0.01, then we are able to stop our iteration. And in this case, 0.0048 is less than 0.01. So our eigenvalue would be lambda here. Lambda equals to 9.0705, and our eigenvector V would be this one here, 0.61891. Okay, so using the power method, we managed to get the dominant eigenvalue and the corresponding eigenvector. Okay, in the second example, the question says determine the dominant eigenvalue and corresponding eigenvector for matrix A. Now, the question doesn't say that you are supposed to use the power method. However, the clue here is the word dominant eigenvalue. So to find the dominant eigenvalue, we've only learned how to use the power method. And so we are going to use the power method in this case. We will start with when I is equals to 0. V naught, the initial vector, is given as 0, 1, 0. And in the second step, we could calculate AV naught, which is matrix A is given as -2, 1, 0, 1, -2, 1, 0, 1, -2, multiplied by 0, 1, 0. I would definitely use my calculator to calculate AV naught. Matrix AV naught would be a 3 by 1 matrix, because this is a 3 by 3 multiplied by 3 by 1 matrix, and we get the entries as 1, -2, and 1. Okay, and from here we could find lambda. Now look, lambda would be the entry with the highest magnitude. So the highest magnitude would be 2, because the highest magnitude is the absolute value of each entry. So the absolute value of 1 is 1, absolute value of -2 is 2, absolute value of 1 is 1. So the highest magnitude would be 2. And we would take the value of the entry with the highest magnitude. So the value of the entry with the highest magnitude is -2. Okay, so I would repeat, the highest magnitude for this vector is 2. And we would take the entry with the highest magnitude, which is -2. Okay, so our new V or V1 would be 1 over -2 multiplied by AV. And we've learned this before using the formula 1 over lambda multiplied by AV. 1, -2, 1. And this gives us -0.5, 1, -0.5. And from here, we could calculate our error. So the infinity norm would be the maximum value of the magnitude of the entry from the current vector minus the previous vector. So 1 minus 1 is 0. I go with the easiest one first. And then we have the absolute value of -0.5 minus 0. So this gives us 0.5. And it's the same for the top and the bottom entry. So we need to continue the iteration up to when the error is less than 0.01. So 0.01 is the stopping criteria. We would continue the iteration. A, multiplied by our new v, negative 0.5, 1, negative 0.5, and we get 2, negative 3, and 2. For the second iteration, our lambda would be the entry with the highest magnitude, which is minus 3. And our new v would be 1 over minus 3 multiplied by this vector. And we would get the answer as negative 0.6667, 1, negative 0.6667. And next we would calculate the error. So this value minus this value, the absolute value of it is 0.1667. And we need to continue with the next iteration. So A multiplied by V gives us 2.3334, negative 3.3334, and 2.3334. Okay, in our third iteration, our new lambda would be this value here, negative 3.3334. And our new v would be 1 over lambda multiplied by AV, which is negative 0.7, 1, negative 0.7. And our new error would be this value minus this value, the absolute value of it, which is 0.0333. And because this is not less than our stopping criteria, we would continue the iteration with matrix A, negative 2, 1, 0, 1, negative 2, 1, 0, 1, negative 2. Multiplied by V, our new V. And the answer is 2.4, negative 3.4, and 2.4. Okay, and the fourth iteration, our new lambda would be negative 3.4. And our new v, 1 over lambda multiplied by AV is negative 0.7059, 1, negative 0.7059. And our new error is the absolute value of this entry minus this entry gives us 0.0666, which is not less than our stopping criteria. So we would continue again. Multiplied by V. This is equals to 2.4118, negative 3.4118, 2.4118. Our new lambda would be negative 3.4118. And our new v would be 1 over negative 3.4118 multiplied by AV. And we would get negative 0.7069. Our new error would be the absolute value of this value minus this value, which is 0.001. Now let's look at our stopping criteria again. our stopping criteria is 0.001, which is similar to the value of our error. However, we would only stop the iteration when the error or the infinity norm is less than the stopping criteria. So in this case, I would continue with the iteration. So in our iteration number 6, the new lambda would be negative 3.438. Our new v would be 1 over negative 3.438 multiplied by AV, which is so the absolute value of this value minus this value is 0.0002. So this value is less than the stopping criteria, which is 0.001, which means this would be the largest eigenvalue or the dominant eigenvalue, and this would be the corresponding eigenvector. So you would always write out your answers as the dominant and V or the corresponding eigenvector is negative 0.7071, 1 and negative 0.7071. And that's it. Okay class, thank you so much for your attention. The power method I think is so much easier than the previous polynomial method, and I hope that you could try your tutorial number 2, and we would discuss that in the next class.